Hello everyone, welcome to a new session of MIST101 presented by UToronto MIST. I'm Nick. In this session, we will keep exploring machine learning. So from last introduction session, half of you voted for synchronous delivery and half of you voted for asynchronous. And last time, obviously, my connection was bad and there were technical issues occurring during live sessions, and video sound quality may not be the optimal during the live sessions, and the time may conflict with your own schedule. So that's why we decided to deliver the sessions asynchronously to provide best quality, and all the videos will be recorded offline and edited into smaller sessions. This is easier for you to view and digest. Any relevant resources will be posted in the video description and on the website. So thank you for your active feedback from last session. We're also giving assignments at the end of the session, so try to finish it in 2 weeks and get a chance to win awards. And please give comments on any question you have about the video topic or the assignments in the Discord help channel. We will respond as quickly as possible. And here I do want to highlight again that this course is slow pace. Since most of you are from first or second years, we will start by getting familiar with the concepts, but not quickly dive into the mathematics and the technicals. So that's why most machine learning courses are in third year. And we are here to focus on fundamentals of machine learning to prepare you for the future studies. It doesn't mean that to take this course and you no longer need to learn anything about machine learning. But you could definitely start to try projects, but this course is mainly about clearing your MIST. So refer to what Sheldon says in his keynote. Whenever you have the hype, just do it. Let's move on. In the last session, we reviewed what is machine learning and its comparison with artificial intelligence and deep learning. So machine learning is the algorithms that learn through experiences. So as the name suggests, a machine that learns. And machine learning is a subset of AI, which is as simple as intelligence exhibited by machines that can be used in a beneficial way. And there's also deep learning, which is a subset of machine learning. So deep learning structures algorithms in neural networks and make decisions on its own. There's another interpretation about deep learning and machine learning, which is deep learning is able to use deep neural network to automatically learn from unstructured example data, whereas machine learning can only learn from structured example data. So for machine learning, data pre-processing is very necessary, which we will see later in this video. And there was another option when we were asking the question, what is machine learning? It's called black magic. I think it makes sense to some degree because there's a term or concept called the black box in deep learning, which means that when you passing the data into the model, you no longer know how the machine model is interpreting the data processing, and you get lost with the algorithm the machine is actually doing. And finally, you get an output. You don't know how that's computed. And we also mentioned the traditional aspect and the machine learning approach of AI. In traditional approach, we write computer programs which maps input to output, and same input will result in the same output. But for machine learning or deep learning, we train the model with data, and the model learns and updates through experiences. Both approaches have advantages and disadvantages. And finally, in the last session, we posted some resources and curriculum, so you can check in the previous video or on the website. Now let's get into today's content. First, we will be talking about the goals of machine learning, and then we will be exploring some terminologies and some common types of machine learning problem which includes the three types of learning: supervised learning, unsupervised learning, and reinforcement learning. And at the end of the session, we will be introducing a very basic machine learning algorithm called k-nearest neighbors. The algorithm is not necessarily a learning algorithm, but in the process of exploring this algorithm, we could get a very, very preliminary view how the machine actually learns and adapts. So at the end of the session, I'll be giving a tutorial which will be using Google Colab. Now, why don't we start with a meme? The interviewer asks, "What's your biggest strength?" So this person, me, I'm an expert in machine learning. The interviewer says, "What's 9 plus 10? I said, "It's 3. Not even close, it's 19. It's 16. Wrong, it's still 19. It's 18. No, it's 19. It's 19. You're hired." Okay, this is clearly a joke about how a machine learning expert is interviewing, but I guess you have a sense that this person is actually a machine who is learning to adapt to the answer. So that is true about how machine is actually learning through the process. It learns through updating itself and adapt to giving out the answers. And we'll move on to the goal of machine learning. The first question into machine learning field is that, what does the machine learn exactly? Is it learning a model, an algorithm to give an answer, or to learn to generate something new? Well, all of these options are possible. This question seems simple, but for us, no matter the machine learning researcher, programmer, developer, or engineers, the goal of the machine learning is very essential to us, since the process to do machine learning is very, very different with the goals. And we will focus on this topic for this session. The second question is around how. Building a learning algorithm is easy, but how do we make sure the machine actually learns and it learns effectively? This question is so complicated to answer. We'll probably spend the whole course to understand and answer this question, how. Well, let me give you some definitions by machine learning by some other experts. First, Arthur Samuel was the American pioneer as the first person to popularize the term machine learning. He said in 1959 that the field of study that gives computers the ability to learn without being explicitly programmed. So this is exactly what we said in the last session. And in recent times, in 1998, Tom Mitchell, who is another pioneer but in a more recent times, provides a modern definition. So a computer program is said to learn from experience E with respect to some task T and performance measure P. If its performance at tasks in T as measured by P improves with experience E. This seems so complex, but the task T is just our goal. For example, to give an answer, to give something new, or to classify, so to perform something. And more importantly, we need to have this performance measure P to see if the machine actually improves through its experience. So, for example, I gave an example of chess playing game from last introduction session. If you are designing a chess player algorithm that learns to play chess, but if you just feed him information about only one board state, then it never really studies to play chess in a full game. So its performance doesn't improve with its experience. Then this learning is not successful. Now, before talking about something else, I don't want to raise too many problems, but the last question in the slide is, how do we measure the performance? Well, these questions I just bear into your mind will be almost everything we explore in the fall semester. I'm spending all this time to get you into the environment and into the vibe slowly. Then we will dive straight into core. So please remember these questions for now. And let me give you a more concrete goal of machine learning. Machine learning goal and usage is to build new or leverage existing algorithms to learn from data in order to build a generalizable model that give accurate predictions or to find patterns, particularly with new and unseen similar data. But how do we understand this generalizability, which is stated here? So in a machine learning problem, we have limited amount of data for the model to learn. In an ideal learning case, the model should perform correctly for all the data it will encounter later, which are unseen during training. So we would expect the model to generalize its function and performance to those unseen data, as that is our initial goal. So here are some interesting memes representing this generalizability. On the left, the in-class teacher taught us that 3 plus 2 equals 5. On exam, he's asking us what is 2 plus 3. Then it would be probably easy to answer 5 without thinking too much. But on the right, if we learn 2 plus 2 equals 4 in class and 2 plus 4 plus 2 equals 8 in the homework, and on exam, the teacher expecting us to calculate the mass of the sun from knowing John has 4 apples and his train is 7 minutes early. Well, this is ridiculous. Well, for machine to learn, it's the same mechanism. If our real world goal is to perform 2 plus 3 or 3 plus 2, then teaching 3 plus 2 equals 5 or some basic addition will be sufficient enough for us to do those kind of simple additions. But if our goal is to calculate the mass of the sun, then neither 2 plus 2 and 2 plus 4 plus 2 help the machine to generalize to our goal. Hence, it is important that we make sure that our model actually learns to generalize to new data from the learned experiences. This is a two-way logic. First, if we want to learn addition, then we should expect the model to generalize to addition. But if we want the model to generalize to the mass of sun, then we shouldn't feed it with addition data. This is the logic here. So we will end the first video here about the generalizability of machine learning, as a generalizable model is essentially the ultimate goal of training a machine learning model. And we will talk about more about machine learning in the next video. Thank you for watching.